The traditional way of making steel in the blast furnace obviously involves lots of coal. And then on the concrete side, 90% of concrete's emissions come from cement. These two industries are highly emitting, but they're both critical. Over the next 30 years, we're set to build double the amount of infrastructure as there is in the world today. And that's the equivalent of adding an extra Manhattan a month.
I'm here with Elliot Brooks, founder and CEO of Cocoon Carbon, which is working to decarbonize both the steel and cement industries. Elliot started his career in finance before founding Thriva Health, and is now working with two other co-founders on decarbonizing both the steel and cement industry. Elliot's calling in from London. Welcome, Elliot.
Great to be here. Thank you for having me.
Tell us a bit about Cocoon and how you started your journey.
Cocoon exists to enable the commercial decarbonisation of both the steel and the concrete industries. And the way we do that is through upcycling the waste or the byproduct from electric arc furnace steelmaking into a low-carbon, low-cost supplementary cementitious material. So it's a bit of a mouthful, but a supplementary cementitious material is a product that can be used to replace and reduce the amount of cement in concrete. And that's really important because cement is the highest emitting component of concrete, and the emissions associated with concrete make up 8% of global greenhouse gas emissions. And so we founded the company in May 2023. My co-founders, Freddie and Will, and I all met on a venture builder program called Carbon 13. And it was Will's Ph.D. research, which really set us on this path of looking at how we could do something with this growing waste stream.
What makes the steel and cement industries so carbon intensive?
Yeah, so on the steel side, the traditional way of making steel in the blast furnace involves lots of coke and coal, roughly 2.2 tons of CO2 per ton of steel. And then on the concrete side, 90% of concrete's emissions come from cement. And cement is made through burning or heating up limestone in a kiln. And that chemical process releases CO2 into the atmosphere.
How does the concrete industry get SCM, or supplementary cementitious material, today?
That's a great question. That traditional dirty method of steel production produces what's known as a blast furnace slag, and that slag can go into the cement industry today as an SEM. The other source of that material is fly ash, which comes from coal plants. And what we've seen as the steel industry decarbonizes, as we move away from coal, these materials, fly ash and blast furnace slag, are rapidly declining, particularly in the west and northern hemispheres of the world. So when you look at the decarbonisation strategies for the concrete industry, the number one lever they have today is to maximise the use of SEMs, supplementary cementitious materials. But that's obviously hugely challenged now because the supply of these materials is falling. And so what Cocoon is doing is leveraging the growing supply of steel slag, which comes from electric arc furnaces, and developing technology that enables that material to be upcycled. So really, we're plugging that supply gap to enable them to continue using SEMs at scale as part of their decarbonisation strategy. They're often incentivized to use SEMs, not just from a carbon perspective, but because they're often sold at a slight discount to the price of cement. Your cost per cubic meter of concrete poured is going to go down quite substantially, and this is a heavily price competitive industry. So it can make a real big difference in their ability to win tenders if they're able to access this material.
Your solution seems really near term. What are some of the other options for decarbonization in the concrete industry?
So there's a few different approaches being pursued. The first, the novel SEMs being produced from alternative materials to blast furnace slag and fly ash. The second is looking at alternatives to ordinary Portland cement and the process through which you make it, using a different feedstock. And then the third would be putting carbon capture onto cement plants. When we started looking at the space, there were kind of three things we thought we wanted to be true, and they were speed. So a ton of CO2 saved today is far better than a ton of CO2 saved tomorrow. Scale. So it's not just about your ability to get to market, really, but it's also about how the wider system requires scaling in order to realize your impact. So do the existing supply chains exist already? Is there existing infrastructure? And then lastly, affordability. So it has to make commercial sense, right? There has to be better reason why someone wants to buy your product over another. And so that is really how we see Cocoon being well positioned to have a meaningful impact.
And what are the key problems that you're trying to solve for the steel plant?
The pitch to them really is around turning a cost center, which is slag handling, into a profit center. It's easy to integrate, quick to get up and running, and there's limited threat of disruption to the steelmaking process.
So Elliot, how do you integrate with a steel plant?
Their core business is obviously producing steel. So really, you need to think about how you do not pose any threat of disruption to that steelmaking. We've come up with the technology, a modular-based system that we can deploy into the slag pit. So this is where steelmakers will tap the slag from the furnace, put it in a big pot, carry that pot, not on machinery, of course, not physically carry, and they'll carry that pot away to the slag pit. The idea of our system is you deploy that into the pit and they tip into the system rather than on the floor. So the main challenge with steel slag and why it's not used today is it has a far higher FeO, as iron oxide content, than traditional blast. And that iron oxide, it requires a far higher critical cooling rate. So our process looks to shift the chemistry, and then we can cool that material far faster. From there, you would just have a dewatering, drying, and grinding step, which is fairly common industrial off-the-shelf technology.
And what stage is the technology at today? Are you already producing SCM?
We're producing around 100 kilos per trial. So we have a TRL5 system. It's kind of the first module we've built, and it's being tested at a research and development steel plant in the north of the UK in Middlesbrough. So we're kind of putting anywhere from 100 to 200 kilos through that system and getting that same amount out of the other end of the process.
How do you think about scaling up the technologies as you go from pilot to demo to commercial scale?
The first is modular design. So proving the throughput for a system up to a certain level, and then looking at how we modularize it. So once you prove them at a relatively small scale, you kind of de-risk the scaling challenges. We're trying to leverage off-the-shelf technology where we can. The second is around ease of integration. We could have looked at deploying the technology next to the electric arc furnace. It would make some aspects of the process easier. But really, that was always going to get a lot harder with the steelmakers' adoption sides. So really, it became, let's deploy this technology and set it up and overcome some of those tougher technical challenges by slotting it into existing slag handling processes. And then on the kind of commercial side, we've taken the decision to narrow our focus and stay, razor focused on just one feedstock type for now. So I would say those are the kind of key ways in which we're approaching scaling and speed and getting to market as fast as possible.
How did you get up the learning curve going from building a company in the healthcare space to something in the climate space?
A lot of YouTube. No, I decided, I want to get back to building and do something new in the climate space. And the more I looked into it, the more clear it became that the hard problems we face require hardware. And that wasn't really where my network was. So that's what led me to the Carbon 13 Venture Builder program. And, it worked because I met a mechanical engineer and a scientist. I really was starting from not much knowledge at all. Freddie and Will probably a bit more than me. But it takes a while, and I'm still learning a huge amount every day on both of these industries. You've got to try and plug that industrial knowledge gap. So we did that for advisors initially, and now we're building the team. We're hiring people who have worked in both of these industries and have really good, strong technical and commercial knowledge.
So you and your co-founders have quite different backgrounds. Can you tell us a little bit about what they've worked on in the past, their backgrounds?
Will is a geochemist by background, and really it was some of his research into how industrial waste streams are changing as a consequence of the path to net zero. He'd spent a lot of time looking at blast furnace slag and how these historic heaps of that material were naturally mineralizing atmospheric CO2. So he kind of had a few ideas on how you might valorize these changing and growing waste streams and byproducts. And that was kind of genesis for Cocoon. And then Freddie Scott was a mechanical engineer and kind of inventor by background. And he had worked on a project around making green hydrogen production scalable. And one of the big challenges is lead times, supply chain for what you would need to produce green hydrogen. So the solution he was working on was around leveraging off-the-shelf equipment, which again kind of ties into some of the design approach we've taken at Cocoon to support the kind of speed to market.
So how did you, Will and Freddie, know that you were a perfect founding team?
Oh, it's very generous of you to say we're perfect. Thank you. I think there's a few things. Like you fundamentally have to get on and enjoy spending time with each other. Values alignment as well. So we sat down and talked about what was important to us in the company we would build. And I think you also have to have similar levels of ambition. So you need to all be aligned on what you ultimately want to achieve. You might not know how you're going to get there, but you should all have a similar common goal. So I think those are pretty critical things. And then the fastest way of figuring out if it's a good fit is to just start working on something. It doesn't have to be the thing that you're going to do forever, but just get to work with people on tough problems and figure out how they bounce ideas off you and you off them, and just start doing something to really gauge whether it's a good fit.
What are some of the lessons you're taking from your first startup to Cocoon?
The number one thing for me is around how we set pace. And I think a big way you have to do that is by setting one really clear goal that the whole company is aiming for, and then just communicate it over and over again. So I like the phrase, communication is what is heard, not what is said. And so you really do have to you get quite sick of yourself saying the same goal over and over again. But getting everyone united around a common goal, I think is really important, whatever the size you are, so that you can then start giving autonomy to the team in terms of how they get there.
What advice would you give to first-time founders?
Build a network of people who have been there and done it before. I think that's so helpful. Like I say, this is one example of a few kind of scaling challenges that you can actually preempt if you've been there, seen it, and done it. But also just to not be afraid. It's a great learning journey. And, if you've got the growth mindset, then I think you'll really enjoy the life, as tough as it can be sometimes.
Thanks so much, Elliot. It was great having you.
Thank you so much for having me, and see you soon.